Hello, Denver X-Ray Conference 2020. My name is Brian Jones. That's my picture you see in the upper right. I will be the presenter today. I am the product manager for North America for X-ray diffraction. I'm based out of Madison, Wisconsin, and today I'm going to talk about the new innovations that we have made in our D8 Discover platform. This is called the D8 Discover Plus diffractometer. So the D8 Discover Plus, a lot of the innovations were built kind of on top of our already existing successful D8 Discover. And we're really referring to the D8 Discover Plus as the top of the line, the premium class solution. You see here an illustration of one of the configurations that's possible. So when I say D8 Discover Plus, what exactly makes it plus? I've tried to list out the most important things, and that's kind of what I'm going to talk about mostly today. Number one, we have enhanced the theta-theta goniometer of the D8 Discover. It is called the Atlas goniometer. We've added a non-coplanar arm option for in-plane diffraction. We're focused mainly on two of the higher end sources, the IMUS microfocus source with the new Montel Plus optic, and the turbo X-ray source, the TXS HE, where the HE stands for high efficiency, and this is a rotating anode source. One of the new stages we made for this system is called the Compact UMC Plus 150. And there are a number of dedicated optics. One of the ones I'm going to focus on is the Pathfinder Plus optic on the secondary side. And finally, the detector, the high-end detector, is the Eiger 2R 500K detector, which we highlighted and talked about at past Denver X-ray conference shows. So let's go ahead and get started here. So this is a representation of one of the D8 Discover Plus configurations. And just to give you an idea of where everything kind of fits in, the X-ray source there is on the left. Following the source, I can have a number of different snap lock modules. We call those modules snap lock optics because they can be removed and replaced without alignment. And there's a snap lock lever that holds them in place against a kinematic mounting surface. So that means that these optics can be installed in seconds and no alignment is necessary at all following that. Of course, we're using the Atlas goniometer itself, and I'll talk a little bit more about what that is in a minute. You see the stage. This particular configuration has the non-coplanar arm installed. And then on the secondary side, I have another snap lock optic position, and finally the detector, which is the Eiger 2. So the first thing I wanted to talk about, and it's the first thing on my list, is the Atlas goniometer. So this is a newly designed goniometer. It is much more robust. It is still maintenance-free like our other goniometer design. It has very highly reinforced primary and secondary tracks, an improved counterbalance design, and the point here is that it's able to very easily handle larger sources, detectors, that non-coplanar arm, and even the larger stages, while not just maintaining the same accuracy, but actually improving upon it. So I'd like to show a short video. So this is showing you that reinforced track on the primary side, the blue ring that represents an Atlas goniometer, and you're seeing the counterbalance design where the counterbalance weights are positioned a little more forward than they were before, which really allows us to counterbalance a lot of the torque and heavier weights that we put on the instrument. So I talked about even improving the old design in terms of angular accuracy. We also have improved in terms of spatial accuracy. So for a long time, Bruker has featured a guarantee on angular accuracy using a NIST certified standard. We're actually able to improve on that guarantee over the entire angular range and certify that we will hit equal or better than plus or minus 0.007 degrees. And this is at any measurement height, any stage, any diameter. And then spatial accuracy. Spatial accuracy is, if I'm using a spot X-ray beam. And a lot of times we want to make that X-ray beam very small. So maybe it's 100 microns, maybe even smaller. So as I sweep through all of the angles I want to look at, this is the degree to which that X-ray beam stays right in the center of the instrument. And we've made some significant improvements in both the equatorial and axial direction of that beam on the sample position. So you can know that whatever angle you're at, you're always probing the same position on the sample. So the non-coplanar arm, this is one of the bigger additions to this, and I'm showing the Atlas goniometer with the non-coplanar arm, and the arm is kind of circled in red. So you have both our standard theta-theta geometry for doing all the standard measurements, but we've added a third goniometer axis. So this is called 2 theta NC, or non-coplanar. But it's extremely high accuracy. So it's approaching accuracy of the goniometer axes themselves. It has direct encoder resolution of 0.00015 degrees, and it's still able to swing over quite a range of angles from -3 degrees to 150 degrees. And the purpose of this is to really allow you to probe parallel to the sample surface. And in this case, generally speaking, your samples here are very thin films where you're wanting to put the scattering vector in the plane of the film. So this kind of shows you what the motion of the theta-theta standard geometry would look like. And then if I add that 2 theta non-coplanar, that's the direction that that non-coplanar arm would move in. And to give just a little better representation, I've now put actual components on the instrument, and you can see it swinging in the coplanar geometry. I'm probing planes that are maybe parallel to the surface or slightly tilted, but the scattering vector is always normal to the surface of the sample. And if I switch to non-coplanar geometry, now I'm moving my detector with the non-coplanar arm. And so my scattering vector is either in or very close to being in the plane of the thin film sample. And so I'm probing planes that are in the plane of the film. So let's take a look at how that works. So this is your standard theta-theta geometry. So my scattering vector is normal to the film. And then I'm going to come back down and I'm going to use the non-coplanar arm to move my detector such that I am looking in the plane of this thin film sample. And you can see how that sweeps through quite a wide range of angles. So looking at some of the more higher end sources for the D8 Discover Plus, the one you've seen in the video so far and the one I'm kind of highlighting here is the IMUS microfocus source. So this is a source that we've offered for quite a while. It has extremely good performance for samples that are millimeter, centimeter size, so very common sizes for materials research institutions. We've added a new Montel optic that is integrated with this source. We call it the Montel Plus optic, and it captures a very large solid angle of the X-rays coming out of the source and collimates it in both directions very efficiently. And because of the nature of this source, the cooling needs are not so much, and so we cool it by just using air cooling. So no water is needed for this source at all. The other option is the TXS-HE. This is the rotating anode source, very high focal brightness. This is because we're spinning the anode. It does use water cooling here. And the beam that comes out, this is more of a line focus. So the beam that we're getting out is maybe better suited for larger samples. And the anodes can be more easily switched. Copper, chrome, cobalt, moly, and several other anodes are available. But realize that there will be some maintenance budget that's required with all rotating anodes. So taking a quick look at the source itself installed on the system, you see the source, the Montel optic, and even the little fan that is responsible for the cooling. And this is the snap lock optic that actually comes after the source, so I can further condition the beam if I want to. And that gives you an idea of how the snap lock optics work. So what are my benefits of this source? Well, as we've kind of talked about already, it's very high brilliance. It's a point focus source. So the beam that comes out is symmetric and it's a spot beam. And it's a very green design, so very low power, no water chiller, no external water needed. It's got an extended component lifetime because it's low power, it's very stable. And as I mentioned briefly before, we've outfitted it with a brand new Montel Plus optic. This is a side-by-side graded multi-layer mirror, but made it longer so that it intercepts more of the beam and produces a beam size that's very well suited for all applications, and also very well suited to couple with other optics like channel cut optics. And it's extremely well suited for in-plane diffraction. So just looking at an example of in-plane diffraction using the microfocus source compared to a more typical configuration. On the top left, I show just a one-dimensional mirror. This is using a standard line source. This comes out, and I need to collimate the beam in the in-plane direction with something called an axial solar. This is many foils kind of stacked together. And it's a bit inefficient at collimating, and it also can cause a significant intensity loss. But that's my only option for this kind of a measurement. If, on the other hand, I'm using the Montel Plus, you can see that the axial solar isn't needed because I've already done that collimation with the Montel Plus mirror itself. And looking at a single peak in plane, you can see that the IMUS with Montel Plus is able to achieve much, much better resolution. So I'm actually even able to resolve out the K alpha 1 and the K alpha 2 components of this peak. Whereas with the standard tube configuration, the width of the peak is more determined by those axial solars that you're using. And so the intensity is actually better with the IMUS, and the resolution is significantly better. So one of the stages I could use for this in-plane diffraction, new stage here, is the compact UMC Plus 150. And I'm not listing out all the specs of this stage, but it is a motorized XYZ stage, and it has infinite phi rotation around the sample normal. And the 150 kind of stands for the translation range in X and Y. So it can actually handle quite large samples, 6-inch, 8-inch wafers, and it can even be used to map smaller samples. So I can have multiple samples installed and automate measurement of each of these samples. Some of the unique features that this stage has are feed-through connections for vacuum, for sample fixing, and also electrical feed-throughs for accessories that require power, like the tilt stage. And I'll show you an example of that here in just a second. So a close-up video, and this is that stage with the tilt stage installed, and you can kind of see where those connectors go. So installing this tilt stage, first we're going to install the two electrical connectors. So that's the tilt along X and Y, and then I'm going to install the vacuum connection here for fixing my thin film sample. And the nice thing about having these integrated, these feed-throughs, is that if I need to rotate the sample in phi, here you're seeing the tilt, but if I need to rotate the sample in phi, these cables aren't getting in the way. I'm not wrapping those around because they turn right with the rotation. So this is a very nice multi-purpose stage that I can use for all kinds of samples, not just thin films. So some of the more innovative optics that we have for this system include the Pathfinder Plus. So this would be an optic that would go on the secondary side. If you remember back in the beginning, there was a snap lock position there that would go right in front of the detector. This Pathfinder Plus is actually an improvement on a Pathfinder optic that we sold before, and it includes a very high resolution beam path. So we have an ACC2, that's an asymmetric channel cut 2-bounce analyzer crystal, and it is able to switch to this beam path automatically. And I also have a high flux beam path. In other words, there's a motorized switch to just a motorized slit, which actually has quite a wide range of opening. I have a one foil automated absorber so that if needed, if I'm using the most powerful source, all I would possibly need is one foil to attenuate the beam. And of course, that's compensated for automatically. And this motorized slit opens so wide because I'm using detectors, whether it's the Eiger 2 that I'll talk about in a minute, or one of our one-dimensional detectors. That slit is able to open wide enough so I'm really able to access a big portion of the active area of those detectors. So finally, the detector itself, this is the Eiger 2R 500K. So this is a result of our extensive collaboration with Dectris. This is a detector that has been available with the D8 Discover now for a few years. But just briefly talking about some of the benefits of this detector, it really represents a breakthrough in sensor design, so that it combines an outstanding active area, very high count rate, the highest count rate available for these type of detectors, very good angular resolution, and support for all common wavelengths. So that takes you from chrome all the way up to moly and even silver if needed. It has dynamic detector optimization. So this is part of the integration with the tool itself, meaning that we have tool and alignment free coverage adjustment. So you can see in the top two pictures, I'm actually able to rotate it between two different orientations to give me maximum coverage in 2 theta or maximum coverage in gamma. And that's dynamically done. It uses toolless rotation and alignment free. And I also have seamless software integration. So the software allows you to switch back and forth between the different modes, 0D, 1D, 2D, and can collect scanning data in any of those modes dynamically in the software. And of course, all the analysis software supports this. So it really is a complete 0D, 1D, 2D solution. So this is your one detector for all applications. And just a little bit more specifically, so I said outstanding active area, it's about 8 centimeters by 4 centimeters. And within that active area, I have over 500,000 pixels. So the resolution is outstanding. In this example, I'm able to take one shot of a corundum plate and I'm covering 40 degrees of 2 theta. If I need more than that, I can always scan the detector. Highest dynamic range. So here I'm doing a reflectivity scan of a silicon wafer in 0D mode, and I'm actually able to cover 8 orders of magnitude without using any absorbers whatsoever. It has a dual threshold, high and low, for achieving the lowest background, and it's a true photon counting detector, so it's extremely sensitive. And finally, exceptional angular resolution, so 75 micron pixel size. If you go much smaller than this, you start to really have to wrestle with charge sharing. If you go much larger, now you're sacrificing something in terms of spatial and angular resolution. So we really feel like this was optimized for the best of both worlds. And you can see a 1D mode scan of lanthanum hexaboride. We're able to get very narrow peak widths. So this is just a quick illustration of how it's able to function as, different mode detectors and have very high performance in each mode. So that's my presentation. I hope this educates you a little bit on what the D8 Discover Plus is all about, and I encourage you to contact me or contact us if you have any further questions.